If you teach high school chemistry, or you are a parent or a family member of someone who's enrolled in middle school or high school chemistry, it's not lost on you that using math and doing computational thinking activities and having those skills is threaded through the entire curriculum in chemistry. And if you're watching, you're a secondary science teacher and you're responsible for or accountable to three-dimensional learning standards like the NGSS or some adaptation, you're looking at using math and computational thinking as a science practice that sometimes gets included or highlighted in our lessons, in our assessment, in our curriculum. But in a nation where our students are seriously struggling in math, with low scores testing, being grade levels behind in math and reading, how do we accomplish teaching so that students learn these skills and core ideas that require math without leaning totally on the math and becoming math teachers? For a long, long time as a chemistry teacher, I thought to myself, I didn't realize I was signing up to be a math teacher because I have many students on my roster who get special ed services and they have grade school level math abilities, or other students who just have been passed through the system but truly haven't learned fundamental math skills. Well, in this video, I'm going to show you how I teach the lesson on predicting ion charge. So we're just about coming out of the Octet rule when I teach this lesson and showcasing it, in fact, as a cause and effect kind of situation, that once an atom achieves its octet, and not yet sharing that it can do so through sharing electrons, but this idea of it's gained or lost electrons, then the effect of that is now we have a charged ion. And so what's a charged ion? What does it look like? And how do we predict what that charge is? I'm going to show you this lesson that is all about using math and computational thinking, but doing so using another science practice, and that is leaning heavily on the development and use of models. Whether you are teaching chemistry in high school, you're a different secondary science teacher, or even you're a parent looking for a better solution for your student to learn chemistry, this is the place to be. I'm Lisa, and I run Lab in Every Lesson, which has become my passion project to just share what I know, share what I've learned through doing in my own classroom about going student-centered as a culture, as a mentality, to craft lesson plans that are very inquiry-based so students can dig in and discover, and most importantly, learn how to discover and learn outside my classroom at any age throughout their life. In the lesson I'm going to show you today on ions and ion charges, it's important to point out that I do have everything mapped to the NGSS and the Steele's Pennsylvania State adaptation of the NGSS as per the standards. But certainly if you're not using the NGS standards or some adaptation of them, the incorporation of these science practices and these cross-cutting concepts are really what's going to bring instruction alive. It's really going to force you out of the lecture lullaby box, if you find yourself living there ever, and do something new. So as we go through the lesson, I will call out to you what exactly is the feature being leveraged, whether it's a science practice or a cross-cutting concept. And if you don't teach chemistry, you'll be able to pick up some tips that way. Now this lesson, ions and ions charges, it falls under the umbrella of structure and properties of matter and specifically connects to the standard that requires students to use the periodic table as a model to predict relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. And if you can see here, this worksheet that I'm sharing with you, it's my entire unit all about electrons, which spans from Bohr's model of the atom and the structure and properties of matter related to that. Then we move to Schrodinger's model of the atom and ultimately get to the octet rule. And incorporating the octet rule is sort of a setup for why bonding is going to happen, because this standard describes the relative properties of elements, where properties are not just physical but also chemical. What we really need to be addressing in this standard is the potential for bonding, the potential for chemical reaction using the periodic table. And certainly there are some hacks to getting to the octet rule that way. Now this lesson, ions and ions charges, it is, as I said, an effect of the octet rule happening, of nature trying to go after this stability where 8 in the valence shell is great. And so that's absolutely a prerequisite to, if you were to use this lesson, I do sell it on my Teachers Pay Teacher store. If you were to use this lesson, or if you're a parent and you're thinking, wow, this sounds great for my child, they really have to know about the octet rule first. And more than that, potentially, they have to be familiar with the Bohr's model of the atom and the simple circles. We also deal here in the electron configuration, so that would be helpful as well. But my lessons are pretty versatile. They contain 5 parts, and so if you are a teacher or a parent, you can swap out parts that aren't so leaning on those prerequisites, if you will. But everything in this unit really has been designed to connect to one another. In so much as chemistry is already a very cumulative topic, we definitely want our day-to-day and our lesson-to-lesson to spiral back on those most important concepts. But here, as we are nearing the end of this unit, I'm going to focus less on the prerequisites as the where we are going. Because after this lesson in my classroom, I also teach about ionization energy and then eventually get to the periodic law. But this lesson on ions and ions charges, the way atoms ionize is consistent within a group. So this lesson in particular will absolutely play into that periodic law lesson, which specifically and totally, completely talks about patterns. And in so much as it is central, patterns on the periodic table, and that's how we're able to use it as a model. The other thing this worksheet shows, you can actually download this. You can grab the link from the description below if you're interested in learning more. There's a link to all of the lessons that I sell on TPT if you'd like to dissect those a little bit, see what's involved there. But what we've got here is a tab for science and engineering practices and a tab for cross-cutting concepts. And this is just for my own self to make sure that I'm satisfying all the criteria, but also outside of satisfying the criteria, really going after as much as I can to make learning as active and as engaging as possible. And so that what you'll see here is that in this lesson, we are definitely, because we're predicting charges and a number, we're applying and expecting students to use math. It's simple math, but still to use math and computational thinking. However, that's going to be a huge train wreck, a highway pylon, if we don't also incorporate the models that they're used to and the visuals. What this also does is it serves all the students in the room, or many of them, those who really do struggle with the math of it, to have a pseudo-tangible, a something to manipulate, a model to manipulate. And then every single one of my lessons, as you can see here, is always about making students active in the process of obtaining, evaluating, communicating information, not in a research-based way, because that's completely impractical for what we need our students to do in the classroom, unless you're teaching in honors or college, like a AP prep kind of course. And then also central is engaging in argument from evidence. These are the 2 pieces, in my opinion, which are solely the inquiry-based drivers of every lesson. If we are not having students get their own data and explain and evaluate their own data and use their own data to support, then we aren't doing inquiry. Then we are just delivering a lecture, delivering rote skill practice. In this lesson, we will also see at work patterns, of course, because there are patterns that emerge in the periodic table. We, at the end of the lesson, will get to our periodic table hacks, which tell us elements in group 1 will be charged +1, and elements in group 2 will be charged +2, and so on. But because we are using numbers, because we're counting electrons, because we are using models to get students through and to that math and computational thinking. Scale, proportion, and quantity is definitely also front and center here. It's all about the amount of electrons versus the amount of protons, where the electrons came from. System and system models, because we're using and developing models, that cross-cutting concept, that main theme of this is how we study chemistry, this is how we study the world unseen, shines through. And then also stability and change. And stability and change only because it is that cause and effect style. Now, I haven't selected cause and effect here. I probably need to. I really think strongly, like, as long as you are using all components of this lesson, you're tying back to how are atoms achieving their octet. And then once the octet is achieved, that cause, which comes from the need for stability, right? So the need for an atom to become stable prompts a change. The change is the cause that produces the effect that's an ion, plus or minus charge. So there's like so much tied up in this lesson. By the time we get to the end of the unit, you can see here how at the beginning of the unit, we're touching on several and many diverse cross-cutting concepts, but by the end, it's so integrated, all the pieces, to understanding and really applying that periodic law, which is our end goal. We are going to include 5 parts to this lesson. So as I talk through them, you don't have to kind of wonder what they are. First and foremost, we always have a review and preview. That's what you might call a bell ringer or a warm-up. And what I strive to do with the review and preview is activate and integrate prior knowledge. So this is where the octet rule is going to come into play and the prior use of those models. Then, super important before we start into the new learning is to set forth some goals. And not just a simple goal, but to give students both the why and the what of what they're going to do and how they're going to accomplish it. So we have learning intentions and success criteria, some of which success criteria are going to be activity-based, others assessment-based. So making sure students are active in class, activity-based, and that they can actually also use that activity to achieve on their assessments. Then we have a learning activity, which is driven in this lesson by an interactive technology-based simulation. Thank the heavens for those people who developed those things, because without it, I couldn't do my job. True story. Always trying, whenever possible, for students to really maximize that obtaining, collecting, evaluating a data and evidence piece. So they're going to populate a huge data table, and then we're going to guide them through, and in this lesson in particular, so many different ways, depending on what your classroom is set up like, depending on how many students you have and their various levels, depending on whether you like collaborative learning or not so much, that you can have students dig into that data to uncover core ideas in a sort of data-dependent analysis way, much like text-dependent analysis, but with numbers and with observations. And then tying it all together with some skill practice at the end. In fact, this lesson even has a little bit of bonus practice. This lesson all in, if you are looking or considering teaching it in a conventional classroom, I'm saying probably 2 periods. Probably 2 full periods to do everything that's in here, maybe even 3. But again, we're trying to tie together so much that time you give your students to think through and work through so many different ways is going to be really important. It's going to be really key. All right, let's get started. The review and preview for this lesson actually is pulled directly from my octet rule lesson. And so definitely, I mean, I'd be remiss to not say it's the advantage to working with an entire curriculum of lessons like this would be that you can pick and choose maybe what you don't finish from the day before. You can start as a warm-up the next day. In this particular example, my octet rule lesson, I often will do the same activity with different elements during the octet rule lesson, and then the next day ask them to do it again, because there is no such thing as too much practice, right? But it's really, really, really impactful when either they're working together on the practice or we're around to support them with that practice rather than just send it home for homework. So what they're doing in this activity is predicting how elements in the third period, a few of them, not all of them, are going to satisfy the octet rule, and what the models would look like when they do, with this driving force being for all the models to look like a noble gas after the octet rule, and that move towards stability has happened. So representing here two metal atoms, sodium and magnesium, also two non-metal atoms, sulfur and chlorine, and then also giving argon as a completed piece, not one students are working with, just as a model, as a goal, where to go to. This is what a noble gas looks like, at least one of them that they'll need. And for more information on how this is, really strategically delivered in your classroom, check out my video on the octet rule lesson, where I dive super deep, another 30 minutes into that one. Next up is laying out the learning objectives for our students. And so what you'll see here is learning intentions and success criteria. It gives our students the why and the how or the what. And so in this lesson, we are learning to use how to use the octet rule. So therein is our packaged, we have to apply prior knowledge to predict ion charge so that we can eventually explain bonding. But do it just like that using the periodic table. And I think if you go back to the other videos in this playlist and you watch this portion of the video that describes learning intentions, you're going to see the exact same ones. The exact same ones. And the reason for that is that's the whole reason to study periodic patterns, to study outermost electrons in atoms, to study properties, is to get to how's it going to react down the line. And that's going to be the case for any content that is very cumulative in nature. We're really tying it all together. Now, the success criteria is lesson specific always, and there's a lot here, which is why I recommended to plan for probably 2 or 3 days on this lesson if you're going to do all the pieces. First and foremost, we definitely need students to come out of the lesson using proper language, so cation and anion, but we, of course, when delivering it, will use the terms ion and ionization as well. Students will use a simulation to build atoms, neutral atoms, and then they will practice making octets, so they're reinforcing that octet rule concept by adjusting valence orbitals. They're doing here, they're developing and using models in this step of the lesson. And then I will have them, as part of it, collecting and evaluating their information that they're doing. They're constantly doing this, collect and evaluate, while they're doing some other science practice. Listing all the particles it takes to build those models in various atoms, primarily Bohr model drawings, because that's what the simulation provides. And then comparing, so we're doing the data analysis there, and the computational thinking with the numbers, comparing the number of protons and electrons in various atoms to determine their net charge, bringing it back to our periodic table patterns, as a periodic table hack, having students argue from evidence what they see in their data that connects to the periodic table, and then ultimately at the end, though, being able to use that cation and anion language when assigning charge. Almost always in my lessons, I give students a nod to some really important terminology. Many times I leave them to discover it. In this lesson, it has to be shared up front. And this might be something you want to actually project while the students are working, certainly because cation and anion are such central ideas here. You don't want them to struggle to remember right away. Just have that resource for them to constantly refer to, and eventually that will, come through. Ions, cations, and anions, of course, positive and negative charges. And if you want to consider this a mini lecture, a mini lesson, go for it. That's what it is. But don't spend too much time here if you're in fact teaching this lesson. Now, for copyright purposes, I have blurred out the simulation because I just never want to get nabbed for sharing somebody else's work and claiming it's my own. It's not my own. This is part of what I do. I find technology and I apply my teacher my teacher magic to it. Here we're using a simulation from a very, very popular provider where students are able to build atoms. They are provided protons, neutrons, and electrons, but they don't need to use neutrons at all. All we want students to do is build with the protons and electrons. And I believe they can only build up to neon, up to 10, because that's how many protons there are there. As they build, they're recording the details of their work and adjusting the valence orbital. You can tell from these task instructions, they're very general. By just reading these task instructions, your students could not carry out the entire process. These are going to provide guidance, and this is one place where you can differentiate instruction for your students by adding more specific instruction or less specific instruction. At the same time, you're going through these descriptions and not demonstrating for them the entire process, trusting rather that they can sort it out because they're smart kiddos. You're going to give them a data sheet, and the data sheet will ask them to do several things. First of all, it's going to outline the elements of interest that you want students to make observations for. Students are going to be able to do it for all the period 2 elements. And then the period 3 elements are in here as well, but they have to really use what they've done with the period 2 elements in the simulation and the observations they were able to make to now project and apply those same ideas to the period 3 elements. So there is here a lot of observe, collect information, but there's also then that apply information built right into the actual activity. Where I'm asking students here first, identify the location on the periodic table, because we are mapping this back to the periodic table, specifically the group number. Because if you teach chemistry, you know that the group number is pretty important to determining charge easily. We want them to list the number of protons and electrons when they build their neutral atom, and then make the valence octet. Again, at this point, they've already learned what the octet is and hopefully practiced a little bit how to achieve it. We want them to record the total number of electrons when the atom has an octet, and this is going to our using math and computational thinking. So they're building the atom, they're making the octet. In this column, they're noting, I lost an electron, I gained an electron. And actually, this column connects directly to our ion symbol. So this is another place where you can differentiate for critical thinking. If you want to remove the ion symbol here as a guidance for what they should be creating, that's a-okay. I include it so that my students get that automatic feedback that they've done it correctly. So that when they're building lithium, for example, they're going to see a lithium symbol show up with a +1 charge. And I believe at the time that I'm recording this, the publisher has updated the simulation actually to show further modeling, to show the number of pluses versus the number of minuses, to really project what the charge on an atom means, right? Because students are going to be so pulled into this idea of loss of electron versus gain of electron to satisfy the octet rule. And since kindergarten, they learned that loss is subtract symbol and gain is an addition symbol. But in chemistry, it doesn't work that way because our symbolism isn't reflecting the process, it's reflecting the outcome. And so this data will hopefully be instructive to your students as they get to what's the charge? +1, but had to lose an electron to do that. The other thing that's going to reinforce that, not just this is what it takes, this is the outcome of making this change. Here's a cause, and this is the effect. Cross-cutting concept. Good thing we checked that box. But also here, tying in the math thinking, the using the math and the computational thinking. As another way to think through this, I have students take their total number of electrons when the atom has the octet. So looking at the model, in the case of lithium, it would start with 3 and it would lose 1. So now it would have 2 electrons with an octet. And then in the next column, taking the number of protons and subtracting from it the number of electrons. if you want to differentiate again and make this a little easier for students, you could label these as columns A, B, C, D, etc. Take column C minus column F and have them do that calculation. But I like to write it out because it makes students aware of exactly what they're doing the math with. They're taking protons minus the electrons at the octet. That's 3 minus 2. And this math will always, always, always give students not just the correct number, but the correct symbol for that charge. So it'll come out to +1. Whereas we'll look at nonmetals in just a minute. It comes out to the -1. And then applying that language, is this a cation or an anion? And they certainly might have to refer to whether you've shared this with them in hard copy or digital copy, or you're projecting it on the board. This is a positively charged ion, has lost an electron. I want to shout out, even if you're looking at this as a word wall and thinking, why is she showing loss of an electron as a chemical equation? That's because I do a chemical reactions and equations lesson at the beginning of the year so that I can show everything as a chemical process before and after a chemical change. This definitely falls into that category of chemical change. All right, now what we're looking at here is just a data sheet for cations where students can observe lithium, beryllium, boron, work all of that data, and then think through or draw out on their own sodium, magnesium, and aluminum. Those are the period 3 elements. Remember, the simulation won't be equipped for that many protons to do the period 3. One thing I love about this is that, especially leaning on models to assist students with using math and computational thinking, is that they always have a tool. They can never just say, I'm bad at math. I don't know it. I don't know how to do this. And as a teacher, I can never say, this student's bad at math, because that's not a thought we allow in our brains if we're trying to be successful in teaching. It's our job to get them there, and we have to be creative about how to do that. So many resources in this lesson should you ever buy it from me. I've broken it down many different ways. So I have these 6, these would all become cations, and then I have a page completely for the anions. So again, they'd go through the 3 from period 2 and the 3 from period 3. And then with that in mind, and this is a huge lesson potential for collaborative work among your students, teamwork, group work, partner work. However you want to separate it in small groups or individuals, there is a slide for all the elements. All the elements. But as a matter of differentiation, did you know that just the sheer amount of activity we assign our students can create rigor? And so I would only encourage you to do individual activities with all the elements if you're going to be out for a few days and this is what your students are going to do in class and you need to eat up the time or something. Otherwise, divide and conquer, my recommendation for the way to go here, especially with struggling learners. In this PowerPoint lesson, completely editable, by the way, I've broken it down many different ways. I do have just the period 2 elements separate from just the period 3, should you not want to have students try to apply it immediately themselves that way. But if you were to separate it either into students who complete anions, students who complete cations, or just period 2, just period 3, you can assign the parts all many different ways, and then have the whole group come together on a shared spreadsheet and share what they found. Then we go forward with this data as a whole group, making sense of it, arguing from evidence, and seeing how that math connects with the models. Okay, I do give one other piece for students here as to prompt. This is the guidance part of guided inquiry. Now, they're going to eventually get into a rote, repetitive way of building their models and making the changes, and hopefully you have some light bulb aha moments. But at the end of it all, they got to look at it and go, where's the patterns? There's a success criteria in the lesson here that says we're going to identify a periodic table hack to quickly and easily use the periodic table as a model for this, to identify the periodic pattern. And so a simple prompt like this could get them there, where you have a sentence and you want them to just fill in the blank. What do you see the difference between metals and nonmetals? And this reinforces what they know already about patterns in the periodic table. Where are our metals? Where are our nonmetals? Which are which? Which ones are always becoming cations? Which ones are always becoming anions? And what appears to be the connection between charge, and I'm pointing them to it. I'm saying there's a connection between charge and group number. What do you see? What they should, of course, clearly see is that if the element lives in group 1, group 1A, it will have charge +1. So column 2 and the second to last column, right? If it lives in group 2A, it will have a charge +2. If it lives in group 3A, it will have a +3 charge. Not so straightforward for our nonmetals, we know, but your more astute students can dig deep and find that. Oh, the group number plus the charge, the absolute value of the charge would give us 8. 7 + 1 and 6 + 2 and 5 + 3. So a little decoding necessary there. In my lesson, again, any different teacher on any different day might deliver this differently. So over the years I have so many different slides to point students only to certain data. This is where, rather than when students are working on their own or in their groups, they can talk about this themselves. But when I'm leading the class, I definitely am corralling just the data I want them to sort through, and the class has a 50-50 shot here. What do you think? And they should very clearly see group number versus ion symbol. And then if your students can decode that, what's the connection between the group number thing, we eventually get to group A plus charge, the group number, and for nonmetals, it's a little bit opposite. Group number -8, right? And so just going through all of those pieces here, I don't want to keep you longer than I already tend to keep you with my passion. Now, I do want to share with you one extra thing. Now that students have been through building the models themselves, which is so important and so should solidify all the other work you've done with them to this point, now you can just let them rip without building it, just referring to it. And this is an activity that honestly for me has started to replace that simulation building activity, because I've done so much model work prior to this lesson. I've been able to just launch right into a worksheet style like this, where I've given again students representative elements from groups 1 and 2, 6 and 7, and then our noble gases group 8, and really emphasizing that piece of the data table. Let me go back to our complete data table, which says total number of electrons and then protons minus total number of electrons. I'm basically pulling out just this part as an additional model-based math problem-solving piece. So and this might be a good homework or follow-up activity, maybe a second day activity, where students are in the understanding that these atoms have already satisfied the octet rule. They've already done the gain or loss of electrons. And now what are we left with? How many protons? How many electrons? There will be imbalance for all of them except group 8. And they're repeatedly doing protons minus electrons, always coming out with plus or minus 1, 2, or 3, and being able to assign that cation or anion designation. This is repetitive practice in the context of our models, which requires them to use math and computational thinking. So it's another tool in their toolbox, because if they've been through the modeling work, they can produce this for themselves. If they've been through the simulation, they can produce these for themselves, even if they don't recall, random regurgitate these formulas we're giving them to solve for charge. And at the end, of course, we want them to do the thing. We want them to use the periodic table to quickly and easily determine charge. And when you're going through these skill practice with them, you can reinforce all the different ways. How do you know? What's the evidence? Well, it's in group 1 and it's a metal, so it's +1. Or we can say it has 37 electrons neutral. It's going to lose that one to get 36. So the 37 protons minus the 36 electrons gives +1. See? Models plus math. And we have 4 or 5 examples of that here. Again, sharing the love amongst metals and nonmetals. There is an exit ticket as well, built-in book widgets, or you can just use the questions and do it your own little delivery way, whatever you love. But I love technology, so when you do purchase this lesson for me on my Teacher Pay Teacher store, you always get a digital notebook, which allows students to work through all parts of this lesson themselves, and it's programmed to show students when they are correct, so there is an immediate feedback. Again, emphasizing that student-centered approach to learning, where students get what they need, and they know what they need, and they know how to follow up with those needs. I hope you enjoyed this lesson. Love if you would leave questions and comments in the chat, in the comments below. And join me where next time I am going to talk through ionization energy trend on the periodic table. Periodic trends and ionization energies using patterns that pop. Thank you so much for your time. See you back here soon.